right, so let's go for it. Inverse functions. Let's try to make sense of them, see if we can work with them. So if I've got a function, and I'm just going to define the function in terms of ordered pairs. If I want to write the inverse of said function, I will write it like this. You might be saying to yourself, wow, what did he do there? How did he make that an inverse function? Looks like he just took what used to be x comma y and rewrote it as y comma x. And that, my friends, is what an inverse function is. We switch x for y. We replace y for x. We fold it over the line y equals x. That's what an inverse function is. So g is the inverse of f if, and I did not spell if incorrectly. When I spell if that way, it means if and only if. Okay, g is the inverse of f if and only if the f of the g of x is equal to the g of the f of x, and they're both equal to x. So if that's the case, if I take x, put it into my f little box here, whatever comes out, I then put into the g box, and ultimately x is my ultimate answer. Works in the other direction too. I put x into the g box first, something comes out, put that something into the f box, and ultimately I end up with the same thing I started with. So the functions undo each other. They don't cancel each other out. I don't like that word at all. So they undo each other. What one does, the other undoes. They're opposite operations. They're inverses of each other. So are these two functions inverses? That's the question. Is this function the inverse of that function? Well, let's find out. Is the f of the g of x equal to the g of f of x? And is that equal to x? So what that means is the f of the cube root of x plus 1 over 2, what's that equal to? So let's plug the cube root of x plus 1 over 2 into my little function. 2 times the cube root of x plus 1 over 2 minus 1. Oops, that's cubed. Right? 2x cubed minus 1. So when I do this, when I cube a cube root, I'm all gone away with, right? So I just have x plus 1 over 2. 2 times x plus 1 over 2 is just x plus 1. So this quickly boils down to x plus 1 minus 1, which is just x. Okay? So we're good in one direction. Let's just see if it works in the other. Is the g of 2x cubed minus 1 equal to x? So is the cube root of 2x cubed minus 1 plus 1 over 2, what's that equal to? Well, 2x cubed minus 1 plus 1 is just 2x cubed. 2x cubed over 2 is just x cubed. The cube root of x cubed is just x. And so, yes, they are inverses. Oh, happy day, they are inverses. All right, so some things about inverses. If f is the inverse of g, then g is the inverse of f. They're inverses of each other. The domain of f is the range of g, and the range of f is the domain of g. They swap places. Domain is the x values, range is the y values. When we do an inverse, we make it all work out. So, and then the last thing, and this is important, if the inverse exists, it is unique. If the inverse exists, it is unique. A couple of things that tells us. One is that a function can only have one inverse, and a function can only be the inverse of one function. That's the one piece, the unique part. The other is this: if the inverse exists, what does that mean? You might be thinking, what does that mean? Does it mean that not every function has an inverse? Well, yes, it does. Not all functions have inverses. So we want to go from there. Let's go big screen. It's cleaner looking. Ooh, much nicer. How to tell if the inverse exists? Sorry about the coughing there. How to tell if the inverse exists? Well, we have the horizontal line test. Here's my original function. This is its inverse. We just essentially folded that function over y equals x. Okay? So if I look at this, is this a function? No, it would not pass a vertical line test, right? So this inverse wouldn't pass a vertical line test, so it's not a function. We're looking for inverse functions. So what we use to tell whether the inverse exists is we use a horizontal line test. So if I draw a horizontal line and it crosses the original function more than once, the inverse of that function is not going to exist. Okay? So that's one way we use the horizontal line test. If we look at this red function here, okay, this red function is going to pass a horizontal line test. Okay, and so the inverse of it will exist. If I look at the blue function, which is the inverse, it's going to pass a vertical line test. Okay, so we use the horizontal line test to tell if the inverse exists. But what if we don't have a graph? Well, we can tell a function has an inverse if it's 1 to 1, or if it's 1 to 1, it has an inverse. That's what if and only if means. Okay, so this function's not 1 to 1 because there's two possible ways to get this value. I can get it there, and I can get it there. There's two possible ways to get a bunch of different values. Okay, so it's not a 1 to 1 function. This function is 1 to 1. There are no repeated y values. Every y value comes from only one x value. Okay, so that's one way to tell. How do we tell whether it's 1 to 1? Well, we tell if it's 1 to 1 if it's monotonic. So if the function's monotonic, then it is 1 to 1. Okay? Good. All right. Questions? None? All right. Oh, there was a question. All right, let's go back. So hopefully the question was, what does monotonic mean? Monotonic means that the function's always increasing or it's always decreasing. Give my penmanship. I don't know why. It's really not me. I think up close it works not as well. So if the function is always increasing or it's always decreasing, then we know that we have a monotonic function. Let's try that out. So this function, is it always increasing? So the way to talk about increasing and decreasing is we looked at the derivative when we were doing that. And the derivative turned out, for this case, to be 3x squared plus 1. And that derivative is always going to be positive, right? If I tried to find a critical number, I wouldn't be able to. I'd get imaginary numbers. So this derivative is going to always be positive. So this function's always going to be increasing. So since this function is always increasing, that means that the function is monotonic. And that means that it's 1 to 1. And that means that the inverse exists. I don't know what that says. The inverse exists. Okay? Inverse exists. All right, so let's try this one. Let's look at the derivative of this one. 3x squared minus 1. Is that always going to be positive? If I looked for critical numbers, I would find where 3x squared minus 1 equals 0. And I'm going to find one, aren't I? I'm going to find it when x equals plus minus square root of 1/3. Right? Okay, which means I'm going to have some intervals where it's increasing, some where it's decreasing. So that means it is not monotonic, and that means no inverse. So if I take a derivative and I could find critical numbers, which would be an indication that I changed from increasing to decreasing, then the inverse is not going to exist. Okay? How do we go about finding an inverse? Well, there's a couple of steps. Step 1, switch y for x. Step 2, sum for y. Step 3, write using inverse notation. So first, let's write this as a y equals. Y equals the square root of 2x minus 3. Then let's swap y and x. X equals the square root of 2y minus 3. Then let's try to solve for y. So the first thing would be to undo the square root. So I would say x squared equals 2y minus 3. And then I would add 3 to both sides. And then I would divide. Okay? And then the last is to write using inverse notation. So if that's f inverse of x equals x squared plus 3 over 2. Swap y for x, solve for y. Some interesting things about inverses. The slopes of inverse functions are reciprocals. So these two functions are inverses of each other. Verify it if you like. Okay? I want to find the derivative at 4, comma 2. So I want to find, the value of the derivative when x is equal to 4 and y is equal to 2. So the derivative, remember this is like to the 1/3 power, right? So I end up with, for a derivative, 1/3, proper, f prime, equals 1/3 x plus 4 to the negative 2/3, or 1 over 3 times x plus 4 to the 2/3. So I want to evaluate that when x is 4. When x is 4, 4 plus 4 is 8. 8 squared, that's what this 2 does, is 64. The 3 says take the cube root. cube root of 64 is 4. So I have 1 over 3 times 4, which is 1 over 12. Now let's go with the inverse. Let's find its derivative. Its derivative, f primed, f inverse primed, is 3x squared. I evaluate that when x is 2. 2 squared is 4. 4 times 3 is 12. I get 12. Notice how those are reciprocals of each other? So there you are. And so that's helpful, the fact that the slopes of inverse functions are reciprocals. It's helpful when we can't just solve really quickly and find the inverse function. So if I want to try to find the derivative of the inverse at 10, well, I can just work with the original function at 2 comma 10. So let's do f primed is 3x squared plus 1. I evaluate that when x is 2, and I get 2 squared is 4. 4 times 3 is 12. 12 plus 1 is 13. So if the derivative at 2 comma 10 is 13, then the derivative of the inverse at 10 comma 2 is going to be 1 13th. Okay? Yeah. That's all. I think that's all. Oh, that's definitely all. Where's he come from? We'll talk about him later. So inverse functions. Swap y for x. Work it out. Monotonic, that sort of thing. As we continue to move forward, see if we can make it work this time. All right. A little shorter. Hey, thanks for watching. Hope you learned something. If you have questions, you know to ask. That's why we're here, to learn and to help. So, thanks for watching. We'll see you tomorrow. Bye-bye.